Hi, everyone. Big thanks to Evan for having me back to the META talk series. Unfortunately, I had a little bit of a scheduling snafu and found myself on an airplane at the same time that my presentation is happening. And so I'm happy to announce that Rafi Hussein and Tarek Abishu will be covering off questions for me, and I'm going to leave you with a recorded version of the talk here. And so for much of my career, I've been working on oil and gas, as many of you know. And a few years ago, we switched over to doing landfill measurements in the lab. And that's been a very interesting journey. And I wanted to tell you about it today, especially some controlled releases that we've been doing at landfill sites to test measurement methodologies and their effectiveness at measuring landfill type emissions, which are very different than those in oil and gas. So I'll share my screen now. And I think everyone can see that well. So I'll talk about full-scale controlled release experiments for, again, investigating the performance of methane measurement tools at landfill sites. So I think that probably everybody knows that the waste sector is a large source of methane internationally, and in Canada, it's close to a third. It lags behind oil and gas. Gas is the biggest source. Um, However, in oil and gas, we've had regulation for some time, and in the solid waste sector, we haven't had national regulation. So most of the waste sector emissions are from landfills and smaller amounts from wastewater treatment and industrial wood landfills, for example. So North America landfills a lot of material. In much of Europe, for example, more waste goes directly to incineration than it does here. And because we put a lot of material in landfills, a lot of municipal solid waste, and then also because we have resource uh, economies, especially in Canada, we have a big resource economy where a lot of agricultural and forest products also end up in landfills. We're at the top, basically worldwide per capita for for landfilling, and that means lots of methane's from landfills. So if we look at Canada's plan to 2030, we have our global pledge reduction target here, which is 30% below 2020 levels. And we have a steady decrease in the yellow, which is oil and gas emissions. And in the waste sector, we plan for reductions, but we don't have regulation in that sector yet. Whereas for oil and gas, we've had it since the very beginning of this plot. So if we move from now until 2030, the reductions will come about 60% from oil and gas and about 40% from landfills, and none from agriculture. And so to achieve that 40% reduction in landfills in only 5 years, or it's 50% reduction in landfills, 40% of the overall total. Our first regulation really needs to be excellent, which means that we need to measure quite a bit. So, of course, in terms of measurement, we have the Global Patrol, and that's helping us understand more things. And by Global Patrol, I mean we have aircraft and satellite eyes on the Earth, not only in North America, but beyond. And that's been really important. In landfills, we're discovering new things. We're discovering, for example, um, that the orange pieces of the pie, for example, that's the active working face of the landfill, the area that we're actively filling, not the covered areas of the landfill, but they're prolific in terms of the emission fraction. So, especially at landfills where we have control systems, so that is wells drilled into the older covered waste. Most of the residual emissions come from that working phase. We certainly don't have collection systems at all sites. The working phase might constitute something close to 80% of total emissions in the US. And in Canada, we see that it's more like 60% probably, from a paper that will be hopefully coming out in the next few months. And if we look up in the top right, we have regulatory methods that we use for management. So we use EPA 21, but a walking version that uses 30-meter grid spacing, and we only walk the covered areas. They don't emit as much, and the red, these highest emitting areas, are effectively outside of measurement-informed management. So we have some gains to make. So the measurement challenge is very different for between oil and gas and landfills. We have very different spatial scale. So some landfills can be a couple of square kilometers in size. Most aren't nearly that big. Most are, from 60 to 120 acres, pretty typical. And of course, they're built high, so they're many tens of meters high, 30, 40, 50 meters high. And with that, we have complex um, atmospheric transport. Basically, we have turbulence on the lee side. It's like a small mountain range. It's like we have orographic lifting. We also have heat from the landfill itself. And so there's significant complexity in terms of gas transport. Emission rates are also high as well. It's not just the spatial scale that's high, but a landfill emissions might be something like a few hundred oil and gas sites together, although we have fewer landfills. Another part of the measurement challenge is the types of emissions we have on surface. So we have point source emissions from the gas control system, from manholes that lead down into the leachate sumps that pull all that organic liquid out of the landfill that we hope doesn't get in there because we have good cap on the landfill. So we have those point source emissions, but then we also do have dispersed emissions. So especially as the landfill settles and as it cracks somewhat, we can have dispersed emissions coming out of surface. And so these dispersed emissions in particular are very hard for satellite and aerial imagers. Not as hard for some other measurement tools like downwind tools like aircraft mass balance and trucks, but the concentration density isn't really there from these dispersed sources to detect them very easily. So anyways, we need to rapidly accelerate the measurement solutions to help address this problem for inventories, for regulation, for triage, all sorts of reasons. So we were asked by Waste Industry Research Consortium, a nonprofit of the US called the Environmental Research and Education Foundation, and they represent the research needs of industry to do controlled release experiments. And so we agreed, and it was very challenging to build this site. I think in that first year, I thought many times that I ought not to have agreed, but anyways, it's in part through great people that we were able to bring into the lab group. We're very accustomed to doing this work now, and we're having a great time running the site and working with the measurement vendors that come and test here. So we call the site SimFlex, a simulation facility for landfill emission experiments, and it's built on an old landfill in Ontario near Detroit. The whole landfill is about 60 acres in size, and it was covered about 7 years ago. It's no longer actively accepting waste and has a great double cover that has very good integrity, and we only have some minor emission points around the edges. Again, around these leachate sumps and some other areas, there's a little bit of flare slip from the waste to energy facility in the top left of the picture. And our release area occupies around 20 acres, and it's sketched out in the red zone here. So we have area and point sources. So the area sources are hundreds of square meters in size. They consist of perforated tubing, just shallowly buried in the surface. And then point sources are flush to surface or just above surface and facing down so that emissions flow off and out to each side over the top of the ground. So we originally installed the system in November 2023 with a 300 kilogram an hour capacity. And that's about what a little bit less actually than a landfill of this size would emit when it's open. And so it was obvious to achieve the right scale of emissions that we had to had to increase the capacity. And so we did that in November 2024 when we installed the system actually underground this time, because the first system was pipelined on surface. And so we've done two sets of experiments. They're community experiments. And I'll just show you a couple pictures of the site, and then we'll watch a quick video, and then I'll come back and describe some results from the experiments. And so this looking from the top of the site, and that's actually the site behind me in the picture. And so you can see some of these elements.
Landfill waste is responsible for about 11% of global methane emissions. As the global population continues to climb, landfill methane levels are expected to increase. One of the most cost-effective strategies to limit future global warming is to reduce methane emissions, which, in the case of waste, requires better understanding of how landfills emit. The solid waste sector's methane measurement needs are unique from those in oil and gas. Landfills are large, emit from different sources, and airflow around complex topography interferes with measurement. In 2023, Flux Lab research group established Flux, the world's only simulation facility for landfill emission experiments, where we evaluate methane measurement tools and validate technologies for the solid waste sector. With support from Environmental Research and Education Foundation, Flux Lab designed and implemented the first large-scale, controlled release study mimicking landfill emissions.
It was really challenging to set it, to design it, and to perform it. Comparing with other control release studies that, for example, were done in Colorado, we are doing 100 times higher releases.
Known amounts of methane are released over 20 acres from both point and area sources by pipeline, with programmable flow controllers. The release capacity is large enough to test satellite and aerial tools, while offering sufficient spatial complexity to assess ground and drone-based tools.
For this year's experiment, we have 13 different methodologies participating. We have truck-mounted sensors doing off-site measurements. We have drones using tunable diode laser systems, continuous sensors that are placed on tripods.
Landfill waste is responsible for about 11% of global methane emissions. As the global population continues to climb, landfill methane levels are expected to increase. One of the most cost-effective strategies to limit future global warming is to reduce methane emissions, which, in the case of waste, requires better understanding of how landfills emit. The solid waste sector's methane measurement needs are unique from those in oil and gas. Landfills are large, emit from different sources, and airflow around complex topography interferes with measurement. In 2023, Flux Lab research group established Flux, the world's only simulation facility for landfill emission experiments, where we evaluate methane measurement tools and validate technologies for the solid waste sector. With support from Environmental Research and Education Foundation, Flux Lab designed and implemented the first large-scale, controlled release study mimicking landfill emissions.
It was really challenging to set it, to design it, and to perform it. Comparing with other control release studies that, for example, were done in Colorado, we are doing 100 times higher releases.
Known amounts of methane are released over 20 acres from both point and area sources by pipeline, with programmable flow controllers. The release capacity is large enough to test satellite and aerial tools, while offering sufficient spatial complexity to assess ground and drone-based tools.
For this year's experiment, we have 13 different methodologies participating. We have truck-mounted sensors doing off-site measurements. We have drones using tunable diode laser systems, continuous sensors that are placed on tripods with metal oxide sensors in them, and of course satellites taking measurements as they overpass the site.
Flux evaluates commercial and developing measurement technologies with quantitative and/or qualitative abilities. Global stakeholders and participants are contributing expertise and measurements that are improving methane measurement technologies, inventory accuracy, regulatory design, best management practices, and global monitoring of landfill emissions, as well as benefiting the management of landfill gas collection systems.
Okay, so now that you have a taste for the scale of the site, I can describe some of the participants that we've had. So quite a number of professional vendors, a few R&D vendors as well, or R&D participants. Um, we have somewhat different tools that we use in landfills. For example, satellites can play much better in the space because emissions for the sites are larger. Means we can recruit more satellites to see landfills than can see oil and gas sites, or they're more likely to see landfills at any rate. We have uh, column sensor drones and also what we call sniffer drones that'll drag a tube along the ground, both of which have good possibility to replace the default regulatory method, which is a version of EPA 21, which is called surface emission monitoring. So we use 30-meter stripes along the landfill to look for emissions. And then we have many of the other same tools that we would use in oil and gas. So if we look at results from the first round of controlled releases, so 0 here is 0% quantification error on the x-axis, and have a number of the techniques, tools, methodologies, solutions arranged on the y-axis here. The grayed areas are our expectations basically for the quality of or accuracy of first order decay modeling. So that's the way that we normally try to simulate the biological activity of the landfill and predict emissions. So they're, if they're less than 50% error, that would be a pleasant surprise, but often we know that they're somewhere between 50% and maybe up to 200% off per site. And overall, hopefully they're better than that once we average out the errors of many sites. But if we look at the quantification tools, obviously most of them fall in between the gray areas, and that means that potentially they're representing site emissions better than the models do on a site-specific basis, and that's a good thing. It's still hard to create an inventory out of snapshot measurements, but at any rate, we see, for example, that fifth from the bottom, truck-based tracer correlation, where we're using acetylene emissions from the surface of the landfill and receiving those downwind along with methane with analyzers that measure both at the same time. That's a very accurate tool. It's difficult to scale in some ways because it requires permits often to emit the acetylene and quite a bit of work to get set up, but it does work very well. So we're near zero bias, and the estimates are pretty tight. So we also have aircraft mass balance represented just above that, and we found that it had a somewhat of a tendency to underestimate here, but at the same time, these emissions or this controlled release experiment was in November. Plumes were pretty low to the ground, as happens at landfills when we don't have a lot of sun. So that lee side turbulence, those eddies will push the emissions down to the ground until they hit a tree bank or something like that. And then we have all the other, variety of other tools, solutions, methodologies represented here. And that's for quantification. For detection, which is what we use largely for management of the surface, and again, we're comparing to walking surveys, the results are pretty interesting. So on the left-hand side, we have an aircraft LiDAR, and so you see that it's 100% true positives detected there. And then we have these drone tunable diode laser absorption spectroscopy column sensors. And so they bounce a laser beam off the ground and it returns to the sensor. They're flying typically between 10 and 30 meters elevation using terrain following. And they did detect some true positives, but lots of false positives in the orange. And that's where obviously there's no emission at the location, but they detected something. And then a false negative where we have an emission present at the location, but they couldn't see it at that spot. So at any rate, that was a little bit unexpected because some vendors have already been selling these services commercially in the sector, even though it's not a regulatory requirement, but it's been useful for operators because it can be done so much faster than walking. So we estimated the 90% probability of detection for LiDAR was about a kilogram per hour, and almost 2 orders of magnitude worse for the UAV column sensors. So they're much weaker than expected, and it makes us wonder a bit what the walking surveys would look like as well. So we hypothesized what the issues could be. They were using sensors without gimbals. The spacing obviously really wide, 30 meters. There's a lot of opportunity for the plume to dissipate to low levels before it reached the path. They weren't using back trajectories in their analysis at all, and so the plume sources may have been substantially off track, off of their survey lines, and they were emulating walking at 30 meters, and so they may have been predicting them in the wrong spots. So anyways, we also, in the second round of controlled releases, just this past November, were able to test the walking surveys. And so this is what a walking survey looks like if we use a sort of a robot dog approach, and his name might be Dave, that's walking the site during emission events. And so we're reporting all the points at 1 second frequency. The intake tube for a small sensor is within 10 centimeters of the ground, and we're judging it in largely the same way. And so the regulatory threshold is 500 ppm. If we find an emission above 500 ppm, it means it's a trigger that something has to be done. And we actually didn't find any at all, even though we had the same number of opportunities to detect emissions as with the UAV surveys. So same number of sources active and same number of experiments we participated in doing the walking. So that was a big surprise. And so we didn't even have enough detections. We had 0 detections at the regulatory threshold to really determine the rate. And if we lowered the threshold to 200 ppm, then we got 1 true positive. So anyways, there in the orange area here, those no emission detected, and no emission at the location, but an emission detected. So that is where emissions are blowing across the ground for some distance, and we're detecting them, and we're only scoring them if the emission is within 10 meters of the path, because if it's any farther than that, it's not necessarily true that a human would be able to go upwind and find it, or may not be willing. We have substantial difference in the way that people do these surveys, and some people are interested in finding everything and some people aren't. So that's sort of the human factor is the orange area there. So the human factor largely determines whether this tool will be successful. Okay, so I just explained this actually on the last slide, and like one of the big aspects of the site is trying to find out why and to make measurement approaches better, and not only with ones that we apply that come out of our lab or that we're using in our lab group, but we like to help others or try to figure out who can help them. And I just wanted to show an example from some of the truck measurements that we made. And so we have some under measurement in specific locations. Basically, we didn't realize why we were underestimating, and we have a Gaussian inversion technique basically that tries to match source locations on site that we guess and rates that we guess, along with concentrations that we see downwind. And we tried all kinds of stuff to try all sorts of actually high HPC supercomputer assessments of reassessments of our measurements with different Gaussian sigma factors and that sort of thing to figure out why we're under predicting. And actually it came down to location. We were always underestimating when we're on this leg. So it's about 2.5 kilometers away from the landfill in blue, and the emissions pass over a forest here. And that's where we predict a lot of these it's in this area that we predict a lot of these low emission rates, and the other parts of the route, the green parts, where we actually do okay, where we're quite close. So anyways, so that's something that we needed to work to fix, and we're doing that now. We've been working on the drone and walking approaches to try to understand that in a mental framework. So anyways, we release all of the data from the site, the whole stack, including the release rates and locations and all the downwind data, winds. And so people are doing CFD modeling with that. It's pretty cool. We're doing our own dispersion modeling. And so this is what some of those releases would look like. So this is release 41 for the people that participated in the first round. And what we see is, like, if we zoom in here, if we do these 30-meter paths across the sources for detection, we're not detecting large concentrations generally. But if we tighten up that path, we go from 48 ppm as the highest that we detected on a 30-meter path to down to a 10-meter path, and we're now detecting over 500 ppm quite easily. You're just transecting through the plume, whereas on the left-hand side there, it's a game of chance. And then 5 ppm, obviously, we're cutting through the middle of the plume and much more likely to detect it. So that's pretty obvious. So if we do that a couple million times and simulate walking surveys, for example, and plumes that are traveling along the ground, what's the probability of detection for a given path spacing on the x-axis and for a given detection threshold? So the 500 ppm threshold, the regulatory threshold in the sort of light blue or teal color, which is along the top here. We see at 30-meter spacing, we might be over 100 kilograms an hour for a probability of detection rate. And that's what we saw. And if we narrowed the path to 7.5 meters, as has been proposed in Canada and some jurisdictions in the States, then the 90% probability of detection is much better. And so if we tune the spacing, it makes a difference as well, but it makes more difference if we tune the thresholds, it makes a difference. But if we narrow the spacing, it really makes more of a difference, makes it consistent. And then the thresholds actually doesn't matter as much what threshold we use as long as we narrow up that spacing. So different jurisdictions specify different walking distances, which actually means that they have different probability of detection rates. And I suspected if we tested all these different spacings of the upcoming controlled releases, this is what we'd find, and we will. We've also done this for drones. So the column sensors that they're shooting a laser to the ground and bouncing back up, they obviously are making a column measurement, and we have some vertical buildup of the plume in the column. And so when we do the column integration, we find that these are different ppm meter values. And so the green is 200 ppm meters. We actually find that the probability of detection rate is on the more sensitive side, the lower values than for walking, which is pretty interesting. And that's because of the column buildup actually helps us detect. And the coefficient of variation in these sensors is they have some noise. They have a CV of about 0.2 to 0.5. Anyways, 100 ppm meters is probably a safe threshold to get them over, outside of their measurement noise by a good amount. So coming back to the controlled release site, so after we made some recommendations to those column sensor vendors, recommended that they fly tighter, they could go higher because those sensors, we tested a number of sensors and they work well even if they're high. We suggested they go faster because they're using faster sensors now, 10 hertz sampling, and with gimbals. Anyways, we're starting to see plumes, which is really exciting, and much clearer indications of leaks. And so if we score those, and so this is again from this past November, the former results were from the November prior. We're detecting predominantly true positives. One vendor detected all true positives, no false positives or false negatives. And the other vendor also did pretty well. Both of them were very sensitive. So, they've brought the sensitivity down by about 20 times to somewhere approaching LiDAR. range, so under 10 kilograms per hour. And so that's a big gain in 1 year. And so it's very exciting, and it's significantly outperformed walking, which is interesting because these surveys are often fast. They're definitely faster, and they're often less expensive to do, and people don't twist their ankles. So if we look at some of the stationary point sensors, so these are very similar or the same ones that are used in oil and gas and trying to be adapted to the landfill context, using dense networks of sensors, so more than 10 sensors around the site. And we had two vendors in the last round, and so one tended to underpredict somewhat, although we have a few higher release rate values that they're underpredicting on. So we don't have a lot of, anyways, I wouldn't put a lot of faith in that. We need some more replication of this. And then the other vendor on the right-hand side, you see that they have a closer to the one-to-one line, although they're also submitting fewer values. They have different criteria for advancing detections to quantification. So anyways, but I think, in general, both of these vendors, again, did reasonably well compared to the walking standard, for example, compared to the models, and will improve, I think, with every time they're back at site. So if we look at their detection rates, so they have a lot of detections and fewer quantifications. So you see that the numbers here are high. So the vendor at the left had around 200 detections, and that also, because we didn't have that many experiments, actually, it meant that there were a lot of false positives. There were some emissions from outside the site, I think, that were being detected. So it was very sensitive, and could maybe be less sensitive in some ways. And then on the right-hand side, we have fewer of those false positives and more true positives. And we were trying to divide the true positives into which ones had been area sources and which ones were point sources. And the approach could detect both. So anyways, for the next steps, we're going to maintain focus on dispersed releases, and on this R&D. We're going to continue to release data, and then we can crowdsource CFD efforts and that sort of thing, and that's already happening, to help us understand plumes and ultimately the measurement methods, and to improve them. So we're wanting to write standard methods for some of the solutions here, that could be used in regulation. And we're going to continue expanding the site, and we'll have a round of experiments coming up this spring, where we're in particular putting emphasis on satellite and aerial imagers. And then we do have another adjunct site under development for satellite dispersed releases. So thanks very much. So Tarek Abishu, who's co-PI of this big effort and a prolific waste sector researcher, we'll answer some questions along with Rafi. And Rafi's the engineer that is organizing all these experiments and has been really highly involved in this effort. So I'll pass it over to them right now. And again, thanks very much for having me, and sorry about the scheduling snafu, but you're in great hands with your questions. And if anyone would like to either come to site or to take part in the experiments in May and June, just contact Anna and the lab, please, and get in touch, and then we'll have you out to site. Thanks very much.